Hello, I'm Jason. Welcome back. Today we're going to play with matches. Do not try this at home. This is a regular match. You strike it on the side of the box, and this is actually a storm match, which supposedly is able to continue burning even if it's underwater or in heavy, heavy rain. So what I want to do is actually burn these under slow motion camera, really get up and close and see what a burning match looks like. And then we'll talk a little bit about combustion and the chemistry behind what's actually happening when something burns. Here is a regular strike match here. And so let's just go ahead and do this in real time. 1, 2, 3. Okay, now for a regular match head, inside the head there's a lot of chemistry going on, but there's a built-in oxygen source inside the match head. That's why it burns so readily. But when you put it into water, you take enough energy away to stop the combustion process. Now this is a storm match here. I'm going to light it and then quickly put it in the water and let's see what happens. Notice how long the flammable part is. It's very, very long, about maybe 3 centimeters. So 1, 2, 3, here we go. And there, it's lit. Now let me go ahead and put this in water. And then out, still burning. I don't know if you can see that on the camera there. Now it's still burning. One more time. It's bubbling underwater. Still burning. A lot of smoke. We can just let it finish off there. All right, so let's get up close and personal with a match head on a really zoom conditions, really high-speed camera to see exactly how matches light and how they burn. Now this is incredible. I have a flame coming from underneath to light the match. When you slow it down, it really does look like an explosion on the surface. Take a moment to look at the vortices and the turbulence in the actual flame itself. It truly is incredible. And just like that, it's over and it simmers down and tames itself. I shot the same setup again with the studio lights off, just so we could see more detail in the flame itself. And man, did that work out nicely. Take a look at the vortices and the tendrils emanating from the surface of the match head. It really looks more like an explosion or a rocket engine launch to me. Here I decided to play around a little bit and put 3 matches one on top of the other so that one could light the other in succession. I think it worked out pretty good. You know, it was pretty challenging to get these shots, to get the flame to look correct in slow motion while at the same time illuminating the match head with just enough light was actually really hard to do. I'd love for you to drop me a line or just let me know what you think of these shots and, you know, just give me your opinion. I just think looking at plasma on this small scale like this is just absolutely fascinating. Once the burning is over, the match head itself looks kind of like the surface of the moon. Now this right here is what I was trying to go for, a close-up zoom shot as the match burst into flame. Take a look at the lower left-hand corner and it really looks like rocket exhaust. And the actual match head itself seems to explode from the inside out. Also, pay attention to the glistening surface that sort of moves around. I think that's actually water being driven out of the wood and the cellulose there and being driven out onto the surface. And it really dances around and bubbles the entire time. This type of shot is why I bought the high-speed camera and why I wanted to shoot match heads anyway. I'd love for you to let me know what you really think. Let's push in a little bit and zoom in before ignition. Take a look at the water kind of glistening and dancing and bubbling. And then the ignition happens, and once it happens, boy, does it go. It really explodes from the inside out. And if you look closely, you can see sort of debris and shrapnel from the match head itself just literally flying out, almost like a deep space launch of a rocket engine. I also think it's fascinating to look at the boundary between the burned and the unburned part of the match head. It's almost like an advancing flame front in like a forest fire or a wildfire. And after the burning is over, because everything is so hot, the water that was beginning to come out really comes alive and bubbles and dances. Now there's actually a pretty fair amount of complex chemistry going on inside of a match head. It's not a single step deal going on in there. So I'm not going to get into the nitty-gritty details of exactly how a match burns. But what I do want to do is talk more generally about burning anyway. Why do some things burn and other things not burn? And why do we have to create friction, like striking a match or maybe holding a flame up to something to get it to start burning? Why is that necessary anyway? So here's our friendly neighborhood periodic table. On the right-hand side of the periodic table are the non-metals. Here's oxygen right here. On the left-hand side of the table, these are all what we call metals. But the typical metals that you think of, like iron and nickel and copper, they're all kind of in the center here. So this red stair step, everything to the left of it over here is considered a metal. In general, metals in a reaction like to give up an electron. I'll talk about why in a few minutes. And in general, everything on the right-hand side of this stair step generally likes to accept or take electrons. They want to suck in electrons. And I'll talk about a lot more about why that happens in a second. Now inside of this match head, there's a phosphorus actually on the striker of the match. But on the match head itself, you have the wood, which is carbon compound. There's carbon right there. We also have sulfur there, and then there's oxygen in the air, and then there's actually an oxygen source bound up in one of the chemicals inside of the match head itself. All right, so matches are pretty complicated with a multi-step process. What I want to do instead is talk about why does everything like to react with oxygen? Oxygen is really commonly reacted with all kinds of things. You hear about things oxidizing. I mean, even your banana oxidizes, or your avocados can oxidize and change color. You know, iron can react with oxygen to make rust. I mean, everything is oxidizing all the time. The metabolic processes in our body is also turning food into other waste products, and in the process, it's reacting with oxygen as well. That's why we have to breathe and get the oxygen in. Now, first of all, if you look at the periodic table, there's an 8 here. That means there's 8 protons in the nucleus of an oxygen atom. So if I draw here 8 protons, that means if this is the nucleus, there's 8 positive protons there. And then going around the outside, now this is a simplified drawing, it doesn't really work like this, but you can think of these electrons existing in orbitals on the outside there. But just keep in mind that drawings like this are never really true. We know that electrons are not dots like this. They don't really go around like a solar system. They're actually wave functions in quantum mechanics, which means they're spread out and smeared out over this region, this spherical region around the nucleus, okay? So just kind of like use this picture in your mind, but just know they're not dots. They're more smeared out in this kind of orbital region here. All right, so in the innermost, you have a shell that can contain 2 electrons, but outside of that, oxygen actually has more electrons. So I'm going to draw them in kind of like an outside, but just keep in mind, in real quantum mechanics, when you really get into what it looks like, it is more complicated than I'm drawing here, okay? So there's a total of 1, 2, 3, 4, 5, 6. Let me change the color of these things here. Here's one, here's one. Here's one. This is just a cartoon. It's not really like this, okay? But I just want you to know that there's 8 protons in the center and 8 electrons on the outside. All right, 1, 2, 3, 4, 5, 6, 7, 8. All right, now, what's going to happen here is that when you look at this atom from far away, there's 8 positive charges, and from far away, there's 8 electrons, which are also charged with a negative charge. And since from a far away distance, there's 8 positive charges and 8 negative charges, oxygen is neutral, right? It doesn't have a charge on it. But it still likes to react. Why does it like to react if it already has an equal number of electrons? In fact, in chemistry, you learn that this column here, oxygen here, it likes to gain 2 electrons to look like neon. Sulfur, in general, likes to gain 2 electrons to look like argon. Fluorine likes to gain 1 electron. Basically, you read the table. This is how many electrons each atom likes to gain. Nitrogen in general likes to gain 3 electrons to look like neon. Why does that happen? Because if my finger is an electron, if I'm far away from this atom, it looks neutral and there's no net positive or negative charge on it. It's a neutral atom. However, if I can force an electron, because remember, electrons are negative, so it's going to repel this electron cloud. So if I can just somehow cram it really close to the electron cloud here and get it almost inside. Think about a swimming pool, putting your face in the top of the pool so you get right up on that level of where that outer shell is. Because this electron is really smeared out as a wave around this area, and so is this one, and so is this one, and I'm left out a lot of shapes and things of the subshells and things. But the idea is when you get an electron, if you force it to kind of like get close to that outer shell, because this electron is smeared out, the atom no longer really looks neutral anymore. Because if you think about it, if you put your finger, if you force it to come here, then you're kind of like in the same level here. And since this thing is not localized, it's everywhere, and this thing is everywhere, and this thing is everywhere, and so on, then suddenly you're right at that level of the outside layer there. And what you see looking in is you see the positive nucleus. You see this being negative charge, positive here. And so because you're at an equal level with this outer shell, you don't really see all of the electrons there. And so it doesn't look neutral anymore, is what I'm trying to say. If you force an electron by physically pushing it against its repulsion into the outer shell, the atom doesn't look neutral anymore to that electron. And the reason is because far away, algebraically, positive, negative add up. But the closer and closer and closer you get, this electron's smeared out. So it doesn't really look like a total negative charge right here. It looks like something less than that because it's smeared out across this whole outer sphere. And the same thing here. So if I force an electron here, it doesn't see a total of like 6 electrons negative and then the 2 here for a total of 8. It sees something a little less than that because this thing is not localized here and it doesn't see the full charge of it. It's like smeared out. I keep using the word smeared out because quantum mechanics is a little weird and we don't know exactly what a wave function actually is, but we do know that statistically, if I measure the position of this electron, sometimes it'll be here, sometimes it'll be here, sometimes it'll be here, sometimes it'll be here in this orbital, but we don't know exactly where it'll be. So if you put an electron here, then over time, it's not going to see a -1 charge because it's on top of part of the wave function. And so sometimes it might be nearby and sometimes it might be far away. And so looking into the nucleus from that position, from that vantage point, it will see the nucleus as being 8 positive charges. It'll see these because these are still inside here. But these that are in this outer shell, it's only going to see a partial negative charge because it's inside the shell with it, is what I'm trying to say. So because of that, if you can force an electron in, it's going to see a net positive charge from the nucleus, 8 positive charges, but it's going to see something a little bit less than 8 negative charges. And so it'll be attracted to this atom and it'll become an ion. So if oxygen gains 1 electron, it will have 1 extra negative charge and then it will want 1 more because this outer shell here can hold a total of 8 charges. That is what one thing in chemistry you learn and in physics you learn is that shells in atoms like this, at least for this shell, all the shells are not the same, but this shell that we're talking about for oxygen can only hold a maximum of 8 electrons. All right, so when the first one comes in and we ram it in place, it's going to see a net positive charge and it'll be attracted in and kind of stick there. And then the next one comes in and the same thing. It's going to see a net positive charge because it isn't seeing all of the charges that are in this outer shell here because it's in there with it. And so it'll can accept another one as well. So the bottom line is oxygen likes to gain 2 electrons because from a distance, the atom looks neutral. It looks like no positive, no negative charge, so it's not attracted to the atom. But as you push an electron closer and closer in and ram it and cram it and force it into the outer shell, it starts to see less and less of those negative electrons that are in the outer shell because it's in there with them, okay? And so it starts to see a net positive charge in the nucleus, which attracts it into place. And it can do that 2 times because after 2 electrons go in here, then no more electrons can fit anymore. And the next one would not even be in this shell. It would be way out in a radius farther away. And so it can only accept 2 before it's done filling those shells. And if you want to know why it can only accept 2 more, that comes down to quantum mechanics and how quantum mechanics predicts how many electrons can fit around an atom. It's basically a lot of math is the bottom line. Now on this side of the periodic table, you have the exact opposite situation. For hydrogen, for instance, you have 1 proton, okay, and then you have 1 electron. which orbits around in that innermost shell. Now, in general, hydrogen is just weird anyway. It can lose this electron if something can suck it away and attract it away. I mean, there's an attraction right here, but if something pulls this thing with enough force, then it can rip it off. But also, for the same reason, if I ram an electron in, it stops seeing the charge, the full charge of the negative electron that's there when it's in there with it. And so it can, hydrogen can accept one more electron there. In general, hydrogen can either lose an electron or gain an electron, but every other element in this row is in general going to want to lose an electron because the outermost electron is weakly held onto by the nucleus. So the bottom line is the left-hand side of the table likes to lose electrons because in the outer shell, there's like only one or maybe two electrons there, and they're very far away and they're weakly held onto by the nucleus. So they can be sucked off by things on the right-hand side of the table who really are good at attracting electrons like oxygen and like, fluorine and chlorine and things like that. So if you put something on the right side of the table with something on the left side of the table, they're going to party because the metal is going to want to give up an electron and the non-metal is going to want to accept an electron. All right? So that's why reactions occur. Now also, even if you have two items on the right, they can still react even though they both want to accept an electron. For instance, carbon dioxide is CO2. Well, they're both on the right-hand side because carbon wants 4 more electrons, 1, 2, 3, 4, and oxygen wants 2 electrons, and they get away with it by sharing the electrons, right? So the bottom line is things burn because that's just one other kind of chemical reaction to an infinite variety of chemical reactions that are out there. And things, when they burn, they're combining with oxygen, and electrons are either being transferred from one atom to another or they're being shared between atoms. And the reason the electrons are transferred or shared is because it's basically going to what we call a lower energy state. It's going to rearrange the electrons in such a way that it's in a lower energy state than it started with. And the electrons are going to move around, and when they move around, they release light. Anytime electrons jump in and out of orbits, then they release photons. So the flame that you're seeing in a match burning is literally because of electrons moving around between substances and rearranging themselves and going to a lower energy state. And when they do that, they release a photon of light. The different colors correspond to how the electrons exactly jump between what energy levels. All right, so the last thing I'm going to say is, we had that match head, but it did not light until I brought a flame next to it or until you strike it and give it some energy like that. Why not? Why doesn't it spontaneously combust? Well, remember what I told you. It's like for the oxygen, right? This is oxygen right here. It likes to gain electrons. But from a distance, this atom looks neutral, so it doesn't look like it's going to attract anything because it's 8 positive charges and 8 negative charges, and so that's electrically neutral. But I told you, if you physically force an electron in by pushing it in and get it basically inside of that outer shell, then the electrons that are there, because they're smeared out, it doesn't see the full charge of those negatives there. And so it starts to see the nucleus as being more positive than neutral because it's basically screening out and some of these negative charges aren't counting anymore, right? But in order to do that, you have to physically push it out there and overcome the repulsion of the electron that's going in with the ones that are there. You have to push really hard. So that's what heat is doing. When I light a lighter and bring it close, that's physically exciting electrons and shaking them and colliding them and causing some of them to get very, very close here so that they can get stuck into place. And that is illustrated by a nice little diagram, which I really like. Okay, imagine that there's this like mountain, which looks like this. And let's say that this is an energy mountain. So this is high energy, and this is low energy, right? And I am right here with like a rock or something like this. Now, the rock, I guess I could kind of like draw it like this and put the rock down here, but whatever, the rock is right here. Now, the rock is high off the ground. If I could get the rock over this hump, then it would go this direction and it would go and go back and forth, back and forth, and back and forth. And eventually, the rock would rest in some final position right here at what we call a low energy condition. This is exactly like a mountain, right? At the top of a mountain, you can stay on top of a mountain, it's totally stable. But if I give a little energy and push off the edge, then it will go tumbling down the mountain and reach some lower energy state closer to the ground. It's exactly the same with electrons because the math is very, very similar between gravity and electric attraction. That's the bottom line. So if you don't think about a mountain, think about electric attraction and repulsion. You see, this thing, whenever an electron from some other substance is far away, this atom, this oxygen atom looks neutral. So it doesn't really want to attract it, and so you're over here. But if you can push on it and get it closer and push it up this mountain a little bit, giving it energy, overcoming the repulsion and getting it here, then suddenly it's not going to see these negative electrons so much anymore. It'll start to see the nucleus as kind of a net positive thing, which will attract and suck it in, and then it will be stuck there and roll down here to the lower energy state. So that is kind of an energy barrier you have to get over when you burn things. If I take this paper, there's oxygen around it. It wants to react with the oxygen. It wants to make carbon dioxide and water. That's what happens when you burn most things, carbon dioxide plus water. It wants to do that. It would be a lower energy state. However, the rearrangement of the electrons can't happen now because there's an energy barrier. And so if I put a flame up to it, then I excite the electrons in the oxygen of the air and also in the paper and get them to collide in such a way that some of them will begin to become attracted to the oxygen and begin the rearrangement process, which then releases some more heat. That's the burning you see. That's the light. And then it's a chain reaction that happens, kind of like a nuclear chain reaction, but not involving the nucleus, involving only the electrons. Once the reaction is started, it releases heat, which then causes further electrons to be able to do that thing, and we call that process burning. So I started out with wanting to just look at what a match looked like under a high-speed camera, and we did that. I think it looks super cool. But I wanted to finish with talking in general a little bit about burning. Matches in general are a little more complicated with phosphorus and other things going on with sulfur, but in general, why does oxygen like to accept electrons? That's what I wanted to get to. Why do things on this side like to donate electrons? That's what I wanted to talk about. I hope you've enjoyed this. Please drop me a line and don't forget to stay curious. Learn anything at mathandscience.com.